So it's time to discuss how to design the computers, the CPUs themselves. Before doing so, let's do a quick checkup where we are in this course and the goals we have. So the goal was to understand modern computer systems. We talked about pipelines we haven't discussed, but we do have talked about memory organizations and virtual physical memory. We have covered all the aspects of multiprocessors, caches, cache coherence, memory models, and synchronizations. We have discussed two out of the three parallelisms that we will cover in this course: memory level parallelism and thread level parallelism. We have not discussed neither GPUs nor vector processing. We have looked a little bit at how general purpose processors are designed, and we have had some discussions about both bandwidth, energy, and cooling, and some other physical limitations that we have to design around when we design new computers. In this part of the course, we will cover most of the remaining areas. We will cover pipelining. With pipelining comes the concept of instruction level parallelism. And we will also look at memory level parallelism, actually a little bit of thread level parallelism as well in a new context. And we will also cover vector processors. Before we start to look at modern CPUs, I want you to at least have seen two slides about the history of computers. As you may know, the first computer is often regarded to be the ENIAC computer, and its designer is often regarded to be von Neumann. We're talking about von Neumann machines, but in computer architecture, we think the two other people were more important in the design of this machine, Eckert and Moseley. And the sort of Nobel Prize of computer architectures is called Eckert and Moseley Award to remember these two people. Their boss was John von Neumann, and he probably got too much credit for the design of this machine. This was an electronumerical integrator and calculator, so that was the name of this. It consisted of 18,000 vacuum tubes. What you see on this picture here is the program. So it was programmed by inserting cables into a big switchboard. 1943 is when they started to work on this during the war. Its job was to calculate trajectories for artillery and so on. Pretty much at the same time, at Harvard University in Cambridge, USA, the machine Mark I and its followers Mark II, Mark III was designed by Aiken. It was built with using different technology. It was an electromechanic machine. Instead of using vacuum tubes, it used sort of relays that use, the ones that says click click when you have the when you want to change the direction of the car and you put the blinkers out. That click click sound, that kind of technology was used to build these machines. John von Neumann, actually with some help from Eckert and Moseley, designed the EDVAC. And this work started in 1947. The new thing about EDVAC compared with ENIAC was that you actually stored the program itself in the memory. So instead of having these wires to define what the program was, you actually stored some representation of the program inside the memory, more along the lines that we're used to today. So that's why these kind of machines are often called the von Neumann architectures. Also in Europe, there was activity on building new computers. Maurice Wilks in Cambridge, he started to work on his computer, EDSAC, in 1949. And Maurice Wilks is actually the first people on this list that I've ever met. He was active in computer architecture until at least something like 10 years ago. So I met him at conferences, and like 3 years ago, we planned on having a large computer architecture in Cambridge to celebrate his 100th birthday, but he died a couple of years short of becoming 100. Konrad Zuse is often regarded to be the first person to build a computer. He also built an electromechanical computer. It was also during the Second World War, but since the borders were not open back then, the world had very little insight in what he was doing. But many people regard him as actually having built the first general-purpose computer. So in Sweden, Sweden was actually way up there in terms of building computers, and we had the first Swedish computer built already in 1950. This was built by a person called Gösta Neovius, and this is the second person on this list that I actually met. It's a good friend of my mother's family. I have spent Christmases and so on with Gösta, but I did not know back then that he actually designed the first computer in Sweden. So I never ever discussed computers with Gösta. So that was a big mistake from my side. This was an electromechanic machine as well, and it was built from relays that Ericsson made. So these were exactly the same relays that was used back then to build telephone exchanges. Since it was an electromechanical machine, it's not far-fetched to understand that Neovius had visited Aiken at Stanford, the person that built Mark I. It was a 32-bit machine, and in addition to 150 milliseconds. Still back then, this was an amazing machine. For human beings and for people in Sweden, this was a big step forward. The next machine, BESC, that one was designed at KTH in Stockholm. Erik Stemme was the lead designer for that. I never met Erik Stemme, but he was actually Professor Emeritus down at Chalmers until maybe 10 years or so ago. He had an office down there, but I never got the opportunity to meet him. This was also built on vacuum tubes, but it also had some silicon in it. Some 400 diodes were also used in this machine. Stemme, he had visited von Neumann in Pennsylvania, so this is not that far-fetched to understand that he was using vacuum tubes. And actually, Sweden sent 4 very promising engineers over to the US right after the war to sort of spy on what's going on there. So Gösta Neovius, he was in Boston visiting Aiken, Stanford. There were another 2 or 3 people of them also in Boston area being stationed at MIT. And then Erik Stemme, he went to Pennsylvania to visit von Neumann. And so this machine was 1953. It was a 40-bit machine, and making an addition to only 45 microseconds. For a short period of time, the legend has it this was the fastest machine in the world. So up until this point in time, Sweden had invested lots of money on these 4 brilliant engineers and also for building this prototype. But since Sweden at this point in time had already had the fastest machine, they decided to cancel the project. Why would you spend more energy and time if you already are best in the world at something? So the whole project canceled. There was a follow-up later on in Lund, SMIL, Siffermaskinen i Lund. I don't know much about it, who was behind it, or exactly what performance it had. They also claimed in Lund, they also claimed that it was the world record holder, but I haven't seen any official statement about that. New thing here was that in Lund they did lots of work on compilers. So for example, they were working on Algol compilers, so moving rapidly from using wires to program to actually starting to use high-level languages here. So I want you to see if you can order these machines in the right historic order, starting with the oldest one. So the right order is ENIAC is the oldest, EDVAC, the von Neumann machine, is the second one, and the BESC machine, the Swedish world record holder, was after that. So do you remember what was the new feature about EDVAC, the von Neumann machine? So it stored the program in memory. That was the feature. So the time before 1990, it was very common that assembler was used by the programmers. So the programmers really wrote their applications straight in assembler. We didn't have that many compilers back then. The high-level languages were not all that good. But most of all, the compilers were not that efficient, so you lost so much performance if you program using a compiler. So the goal here of the instructions of the computer was to sort of bridge the semantic gap between the programmer and the underlying hardware. So people, when they design new machines, were very tempted to design very complex instructions. And the example I bring up here are instructions in the British computer company ICL, where they have, for example, instructions to do arithmetics with pounds, shillings, and pence. And so you had some very, very specialized high-level kind of instructions. And the signum for all this era can be summarized as complex instruction set computers, CISC. Also, the good old x86, the forerunners of that, also saw its day in this era. So this is the time that's been x86 instructions got their inspiration from. The trends today, when you design new instruction set architectures, are quite different. So first of all, ISA stands for Instruction Set Architecture. That is not just one set of different assembly instructions, but it normally constitutes an entire family of computers. So IA32 is the name of Intel's family that is commonly known as x86 as well. So this is x86 is an instruction set architecture. These days tend to last for long periods of time. So back in the ICL days, that computer with punch, shilling, and pence, maybe it was only lived for 4 or 5 years, what do I know? And after that, they came up with a new computer that had new instructions that probably were even more complex and niftier. But now we want the instruction set architectures to last much longer. And there's going to be many implementations of the same instruction set architecture, ranging over 20 years or even more in the x86. For x86, it's certainly much more than 20 years it has been around. We have seen consolidation in the market. We actually have much fewer ISAs today than when I studied computer architecture. ISA was, coming up with these new instruction set architectures was a very popular research topic in academia back then. And 20, 30 years ago, academia also was quite successful in coming up with better instruction set architectures than industry, not least so the two authors of our book, Hennessy and Patterson, were part of that kind of research. But actually, quite frankly, the ISA technology or the ISA, the instruction set architecture itself, doesn't matter all that much today. It doesn't matter if it's ARM instructions or x86 instructions or some kind of alpha instructions that I believe to be much better for some definition of better. It's all market driven. And you can overcome, even if you have a lousy instruction set architecture, you can often overcome that with smart engineers and with good implementation technology. Also, what's new today is that we don't expect sane programmers to do most of their programming in assembler. Instead, we really expect the programmers to use some kind of high-level language, and we use elaborate compiling technologies to produce optimized code that, from a performance point of view, is fairly close to the hand-optimized code that a sane programmer can produce. So topics that you have to cover when you would like to design one of these instruction set architectures are, first of all, you have to find a compelling operand mode that suits your needs. You have to come up with a format, an instruction format. How are you going to represent those instructions in memory? Then you have to start to think about what kind of mix of instructions you have. And most computers today have the same, arithmetic instructions look very similar, add and subtract, but the place where you have to make hard choices in your instruction set architecture is how you like to handle the conditional branches, for example. What kind of addressing mode you like to support, and what size of the immediates that you would like to support in your architecture. You really have to make hard choices here. And furthermore, of course, you can make this list longer, but also what is important these days is to keep in mind that you want your ISA to be implementation independent. You don't want to design an instruction set to only work well for the kind of silicon technology you have exactly this year, but you want your ISA to be implementable, future-proof, implementable in other kind of technologies as well.